Okay, so the tutorial will be mostly a tutorial for me, right? Okay, all right. So what we'll do today is I'll first finish discussing the 10 classes, and we will find the structures of the Hamiltonian in some interesting classes. In particular, we'll understand many of the things that Jay showed, and then what I will do in the second part. This is what I would say as a more theoretical discussion. And the idea here is to understand where these 10 classes really come from. And you will see that when I finish this discussion, that it has really got to do with understanding what quantum mechanics itself is, right? What do we mean by a quantum system? Actually, it will actually go to very subtle points about that. Okay? And then in the second part, all of these 10 classifications, the tenfold classes came from some symmetries. And from these symmetries, we will go into topology, right? And that's so the topology will get hopefully introduced in the afternoon, right? Okay, and hopefully we'll spend an hour in the afternoon discussing topology and so on. And then the remainder of the time we can solve some problems. And I'll put down a list of problems. You already have those problems, which I'm sure all of you have solved, right? And so some of you can present your solutions. I'll put down a few more problems, and then we can take it up. Okay. So let me quickly tell you what I discussed last time. I said that there are these non-ordinary symmetries. Right? So they are these T, and this is what we call as the UA symmetry, and there was a TL symmetry which we call C, and there was a TA symmetry which we call as S. So this is time reversal. And as Rajdeep asked last time, why am I calling this time reversal? This is because I've shown that this is solitary. There's only one such kind of symmetry in the system. And we know that a well-known usual antilinear operator is time reversal operator, and therefore we'll call it time reversal. And the C is what we will call as the charge conjugation symmetry. And S is what we will call as sublattice symmetry, right? In different communities, these may get different names. So let me just make a connection to Jay's language. Jay called this particle hole symmetry, right? That was the language that Jay used, okay? So this is the language I've used. Then I showed you that if a system has this kind of symmetry, then it has to make a choice. That is, T square must be either +1 or -1. It has to choose the kind of system it wants to be. It'll either be +1 or -1, right? And similarly, C will be either, I will just write it like this. I will just write it as C is equal to +1 or -1, right? And the sublattice symmetry, if it exists, it is either 1, and if it doesn't exist, it is 0. And same thing, if T doesn't exist, it is 0, and if C doesn't exist. And that gave us those classes, okay? And our immediate goal after having discovered these classes was to show to find what is the structure of the Hamiltonians in each of these classes, right? This is what we want to find, okay? So I start off by saying, okay, let's look at class A. And class A has basically no additional structure. The set of all Hamiltonians in class A, and I will just put an I here so that we can make contact with the usual vector spaces and Lie algebras. So this was our Lie algebra UL, right? This is what I showed. Okay, then I went to the class A1. This is if you look at the symmetry signature there, this is a system with symmetry signature 1 + 1 0 0. So here we get T square, or T is equal to 1. What that means is the operator T square is actually 1. Okay, and in this system, I showed that T psi dagger, T inverse, can be written as, this is generically can be always written like this, right? So under the action of, I just can put an equal to that, and under the action of time reversal, the electron operator, or the fermion operators, they become this. And I showed that we can always choose UT to be identity, right? This is what I actually showed. And you can also write a matrix representation of this matrix representation of this time reversal operator, and that is actually UT equal to K, and if I put UT equal to 1, it's just complex conjugation, right, if I put this. And based on this, I was able to show that the space of Hamiltonians, the set of all Hamiltonians in class A1 are real symmetric Hamiltonians, right? We found that the condition was H, UT, H, UT dagger is, in this case, if I put this, sorry, there's a star here, star is equal to H, right? Now H is supposed to be Hermitian and it's supposed to be real, so it is real symmetric, right? So you end up with only real symmetric matrices. The set of all L by L real symmetric matrices or Hamiltonians will be the space of Hamiltonians in class A. So you can immediately see that you can always, there is a basis in which all wave functions are real, right? Because the Hamiltonian is all real. Right. Okay, so what is the dimension of this space? Let's just, I went through that somewhat quickly last time. So you see, every Hamiltonian of L by L has some diagonal elements. So let me just indicate them something like this. They are all real numbers. There are L of them, right? And then you have a typical element here will, let's say, call it as HA plus IHP or something. Call it H1 plus IH2 or something, right? So what does that mean? That means that this H2 has to be 0. All the H2s have to be 0. All the complex parts, all the imaginary parts have to be purely 0. So how many independent parameters are there here? You can do the counting, and in fact you can see, you can do a little bit more analysis on this, and you will find that this space, the space of all in class A1 is the set UL. You take out the generators of the these OL rotations, and that's what you will end up as the space of Hamilton. Okay, so that's what happens. Okay, so this is a very quick recap. All right, now let us go to the next class. So the next class, I will go to the other end, and that is class A2. Right? Okay, if I go to class A2, then again I just use exactly that definition. I know that under the action of T, this psi dagger goes to psi dagger UP. Okay, that's just definition. Yeah. It's very easy, no? Because you see, what are you taking off from here? You're taking off from here things that look like that, no? So it is IH2 and there'll be a minus IH2 here, right? So you just remove all of them. So what are you taking out? You're taking some anti-symmetric matrices out of them, right? Just knock the I off. So you're removing anti-symmetric matrices. How many anti-symmetric matrices are you removing? As many as these elements off diagonal, right? Right? Those are exactly the generators of OL. Right? Okay, so thank you for that question, because I'm going to be doing this all along. So I'm not going to stress on this point. I'm just going to just assert it and you can work it out yourself. Okay, all right. Okay, so this is what happens. All right, so now in this class, what is our result? Our result is that T square is minus 1 to the power number of particles. This is what we derived last time, right? Okay, so now can you tell me what will be the equation satisfied by UT? So you have to play the usual game. So what you have to do is you have to do T square psi dagger T minus 2, right? And what will happen if I do this? No, negative signs do not cancel. Yeah, you see, you fell into the trap. Actually led you to the trap. So T square on some n particle state will give you n particle. You actually create one more particle now. And when T square acts on that, it will give you minus 1 to the n plus 1. So you will end up with a minus sign, right? Okay. So if I act this on an n particle state, T to the minus 2 will, it's not transposing. It's a usual operator. So it keeps it in that sector. Now I create a particle. I'm creating psi dagger. I'm adding. So I'm lifting it one. And then when T square acts again, it will pick up n plus 1. So you will get minus psi, right? So you'll actually get minus psi dagger. This is from the definition of this, right? If I go through this process using the other definition, that it is psi dagger UT, what will I end up with? I will get that this is psi dagger UT star. Right? This is by the usual thing which I did last time, saying that time reversal is an anti-linear operator. Right? Krish, I thought I made a mistake. All right. Okay. So this is what happens. So what do you see from here? You see this very beautiful result that ut star is equal to minus identity. L by L identity. Okay? Before you do anything, before you try to find ut and all, you can already see something extremely beautiful here. Right? You will see that L has to be necessarily even. Do you see that? Okay. The trick is, take determinant on both sides. If I take determinant on both sides, it is determinant u multiplied by determinant of u star, but determinant of u is always 1, right, in absolute value. So the square of that is 1, right? Whereas this will be minus 1 to the L, so it necessarily forces L to be even, right? So if a system has to have this symmetry, then L must be equal to 2m. Yeah. Sorry? No. Wait. You're going too fast. Ut is identity for the class A1. We have to find what is ut, what is a natural ut here. By the way, in this class, what is the equation satisfied by ut? It's ut star is equal to 1. It's completely distinct from this, what this guy satisfies. Right? So before finding the canonical representation of ut or the canonical form of ut, I'm just inferring that L has to be already even, right? So this Kramer's degeneracy, what people talk about, is already sort of, is actually giving you a hint that something like that should be around, right? You can see that, right? Okay, so this is what happens. Okay, now can you suggest some way of proceeding to find a natural ut for it? Okay, so what is the smallest dimension of m you can, what is the smallest m you can choose? M is 1, right? So then L would be 2. If L is 2, can you tell me a matrix that satisfies this equation? Where is the gentleman who asked about this I sigma x? Okay, so let me just have a discussion with you. So if I have a 2 by 2 matrix, can you tell me a matrix that satisfies ut star is equal to minus 2 by 2 identity? So, sorry? I sigma x does that, is what you think. I times identity. All right. You want it also to be, you remember, it should be unitary. This thing should be unitary. Do not forget that. So now you are saying, see, you change sides now. You are pushing for I sigma x, right? So one of the things that will do it is this guy. This guy will do the job. Right? I think in our paper we use, I don't remember exactly, I think we use this convention. Right? It doesn't matter, you can choose whatever you want, right? So this is the matrix that will do the job. Okay? So there's a formal way of showing that this is what happens for any m. And that again uses Takagi decomposition. Right? So there's a generalization of Takagi decomposition which says the following. A matrix, a unitary matrix which satisfies this condition, which now I will explicitly write as 2m cross 2m, can always be decomposed in the following way, right? So ut can always be decomposed as A, J, A transpose. What is J? J is simply the generalization of the sigma x matrix with m entries, if you like. So what does J look like? J is equal to 0, 1m, minus 1m. Right? So this is again Takagi decomposition, right? It's just theorem in matrix algebra. All right. So what does this mean? This means that I can always go to a basis, right? Again, you have to use that basis transformation trick. I can always go to a basis where ut is chosen as J. Right? So what that means is that the canonical ut is equal to J. That's what I've concluded. Right? So now it should not be now you should not feel uncomfortable if someone says that, oh, time reversal operator looks like I sigma y. And of course, if I write now the time reversal matrix, again, you can just work this out yourself. Time reversal matrix will be this J times K, the complex conjugation. If I were to write the time reversal matrix in first quantized language, you will get this complex, because it's an anti-linear object. Okay, everybody's good with this? Okay, all right. So with that statement, let me just show you what would be the structure of the Hamiltonian. The structure of the Hamiltonian now is very simple. So I want to find what is IHA2. What is the space of all of these Hamiltonians? So what you'll find here is that these Hamiltonians, they will satisfy the following condition. Sorry. This is the condition that they have to satisfy. Okay, we can put this like this. So if you work that out, and I will not bore you with the details, you will find that the Hamiltonians have this kind of a structure. Right? So what you'll get is, you'll get an m by n Hermitian matrix here. You will get another matrix here, and the one across, diagonally across, would be negative the star of it, right? And this guy will be the complex conjugate of this matrix. Right? That's the structure that you will get. And if you look at what is the vector space that you will get the unitary group, the unitary Lie algebra, and you take off from it, you remove from it the Lie algebra of the symplectic group. That's what this guy will get rid of. Right? So you see, the important thing to remember is that both of these guys are no longer Lie algebras, because these will not, under the commutation, they will not close. Right? That's what you will get. Right? Do you know what this structure looks like? Have you seen this kind of structure before? If you have heard of quaternions, you might see that there's something to do with quaternions. If you have heard of it, otherwise it's you can just Wikipedia it later. Okay. All right. So you see, so I found the structure of this place. Yeah. Sorry. No. It's not the A's and R's in the previous case. No. There is a connection. Of course, there's a connection. It is what leaves that guy. It is the kernel of that object. Right? You see what I need. Right? So what I need is, what is the condition? The condition is that ut is the. Okay. Let me just go back to here. Okay. So here, what is the condition? It says that h star ut dagger is equal to h. I'm just repeating this, and now that becomes 1 h star is 1 is equal to h. So what is this saying? This saying that certain elements of this matrix have to be 0. So it is something in that. So you can write that matrix as whatever remains plus something else. So A, when acting on that something else, must kill it. Right? So it, in some sense, is the kernel of that. So that's why it continues to be a vector space, because this is a homogeneous equation in H. Right? So it continues to be a vector space. If I have two of these things which satisfies this equation, any real linear combination of them will also satisfy this equation. Right? When you go to the interacting systems, this will not be true. Okay, other questions? So everything is more or less clear now? What's happening with these two things? Okay, all right. So now let's proceed with the next class. So I'm going to go to the class where we introduce charge conjugation, right? So the charge conjugation, the first class is D. Let me go back to the other picture. That is, where did I put that? Okay, I'll find it. Sorry? Okay. All right. Okay, so let me go to this class where we have the charge conjugation matrix, right? So I have the charge conjugation operator, and under the action of the charge conjugation operator, so I'm going to class B now. So what happens? This guy goes to psi UC star. This is again a unitary matrix, and since it's transposing symmetry, I have to take psi daggers and make them into psis. Okay? All right. Okay, if you go through the algebra, you will find that you have anything that satisfies, again, what is the condition on this? This is condition is c square is minus 1 to the n. Right? This is what we have now. Right? Sorry, c square is 1, c square is equal to 1. This is the plus 1 signature, right? This thing. Okay. So if you do that, you will find a very nice result again. You will find that UC star is again identity. Okay? Everybody sees what I'm, okay, we may not see the algebra, but you have to see, you have to just understand what I have said. So you will find this result if you go through this our usual trick of taking c square and all that. You will find that it will satisfy this condition, right? And what is the symmetry condition? The symmetry condition is the following, right? UC H star UC dagger is equal to H. This is symmetry condition. Now it's very clear that if I have something like this, I can do exactly the same Takagi decomposition. And remember that if I do a basis change, right? If I go to some other basis where it's u tilde c, you will find that again this guy will transform like this. This is how the u will transform. Not as a dagger, but as a transpose. Okay? So you have to remember this and you have to remember this, and then you will immediately conclude that the natural UC for this is identity again. Right? This is again, UC is again identity. All right. Now I want to find a matrix representation of this charge conjugation operator. Just like I did the time reversal, I wrote something like this. I want to find a matrix representation of that. First quantized representation of the charge conjugation operator. Well, that's not hard. What you do, you just log this off, put a k and put a k here. Right? So you immediately see that the charge conjugation, this is the matrix, looks like this, right? It looks like UC times K. So now this must be very surprising to you. Why is this surprising? Oh, you're not surprised? Right, it looks like time reversal, but that's okay. But you see, this is a linear symmetry. Charge conjugation is a linear symmetry. Look here, it's transposing linear symmetry. In the abstract, symmetry is linear, but its representation is antilinear. Right? It causes a lot of confusion, at least it caused me confusion when I was reading the literature, because people use sublattice, all this very interchangeably. In some places they say it's linear, some places antilinear and so on. So the bottom line is the following. The abstract symmetry, this or the operator, the charge conjugation operator is a linear operator. But because of the transposing nature, its representation is antilinear. Right? Yes, Chetu, it's a little counterintuitive. Antilinear. I've just showed you. Yeah, my hands are clean. As only chalk powder. Yeah. No. You will not get the transposing nature in the matrix, no. No, the transposing nature will come in the operator. Here, so dagger has gone. This is the matrix representation. Like how if I want to see, if I want to use column vectors of matrices, what will I do? That's what. So the transposing nature shows up here, and the transposing nature also shows up in the symmetry by this minus sign. So you are asking, if I just take a one particle state and hit it with this, what does it do? So actually what you should remember is that is taking you to a whole state. Right. You can view it like that, or you can just, that's fine. Yeah. Yeah, there is a tau x kind of term. We will actually use that idea later. Yeah. Yeah. Any other questions? Okay. Very nice. So now we ask the question, what are the space of Hamiltonians? Oh, this is very simple now, right? So you will see that UC is equal to identity now. So you will see the condition is that minus H star is equal to H. These are all the space of Hamiltonians in the class D. Right? Right? So what will be the Hamiltonians? The Hamiltonians will have only imaginary terms and it will be Hermitian. So it will look like the following. It will look like the H fellows will look like. So there's a matrix. You can take an overall I out of it. There'll be some stuff here. This is an anti-symmetric matrix. So there's some stuff here and this is minus of the same stuff. Just copy this wiggle here. Right? That's the matrix. That's the kind of matrix you'll have. And this is Hermitian. Right? So what is this? What is this? What is this space? The set of all of these guys. What is that object? I have already shown you. That is OL. Right? That is OL. So that's what this entry is. Okay? Everybody's good with that? All right? Okay. Now, I will not belabor this point any further. What I will do is I will say that the class C, which comes with symmetry signature 0, minus 1, 0, has C square equal to 1. You can go through exactly the same procedure, right? And what you will find is that the canonical UC is J again, just like the time reversal, right? And you will find, but the structure of the Hamiltonians will be different. In fact, you will find that that is the USP2M group. Right? You will find that that's the group of, that's the symplectic Lie algebra. Okay, this is a story. Okay, so until here, things are pretty straightforward, and many of you would have seen at least these two classes. You have seen it in many other courses and elementary courses, right? The interesting stuff happens here and all the way below, and these are called as the chiral classes because all of them have sublattice. Okay, so before I discuss sublattice symmetry, if there are any questions, I'll take them. Yeah. That I will not be able to proceed. T square is equal to minus 1 to the power n. That equation is true for any particle sector. N, where L is not the number of particles. L is the number of states. L is not the number of particles. Right? L are the possible states. You can populate the states with any number of particles starting from 0, 1, 2, all the way up to n, all the way up to L. But this is not the number of fermions in the system. It's the size of the Hilbert space. L. Where have I? It's L. Okay. Yeah. Okay. That was a little. I was a little jarred by that, but okay. All right. Okay. Yeah. Ah. We'll take it up later. We'll definitely. I mean, that's a very interesting question. We'll come back. We'll take that up because it will definitely take us out of what we want to discuss. Okay. All right. So maybe tutorial you can ask this question after I've done what I have committed to do. Okay. All right. Okay. So now let's go to the class A3. Okay. And this is the really interesting class because this is something that we are usually not used to seeing in condensed matter, although we use it all the time. Okay. So this class does not have time reversal symmetry or charge conjugation. It has only this strange thing called a sublattice symmetry. Right? So let's understand what is this sublattice symmetry. So in the abstract, as an operator, S is a transposing antilinear operator. Right? Okay, transposing. Okay. So let's see what is the action of S on some electron operator or fermion operator. So it would be something like this. We will just write it. This is just definition, nothing more than that. Psi transpose US star. This will be what we will typically do. Yeah. Okay. So remember, I showed you that S square was equal to what? You remember what I showed you? Sorry? No, I said that we can always set it to 1. It was e to the I theta L, right? Right, exactly. So it was shown that this was e to the I theta L times number of particles. This is what we actually showed it was, right? And theta L was equal to 2 pi little l by L. Okay? Everybody's good? Right. Okay. Now, if I go through this process of taking S square and playing this game, what do you think my answer will be? What is the constraint I will get? I will get the following constraint. Okay, you can work this out. This is just very straightforward algebra. This is what I will get for this US times identity. Okay, this is just, take me on faith here. Right? This is true. So now suddenly you see, you can do a Gates transformation of your basis, or you can simply redefine this US, right? Because what you can do, actually, no star will be there. Sorry, this star will not be there. This star will not be there because it's actually a, okay, sorry, let me just take a step back. See, when I do this for the first time, I will get this. When I do it the second time, what happens is, this is actually a anti-linear operator. So that star will be gotten rid of, right? And this is the result that you will get. So what I can do, you can immediately see that I can redefine my US, whatever I had defined to be, just absorb one factor into one of them and the other factor into the other one of e to the I pi by L, and you can always reset it to be US square equal to 1. Right? So this means that I can always choose S square equal to 1. Okay? It's not a distinct choice. Okay, very nice. So what do I have here? I have a matrix whose square is identity. Right? And it is a unitary matrix. Okay. Can you tell me a solution for that equation? Generalization of polymetric, maybe, okay. Almost any matrix would be okay, maybe, I don't know. All right? Sorry? Okay, this is actually very easy to see. So, what is the result here? So, you will see that US is equal to US dagger, right? Because it's unitary. So, it's unitary and Hermitian. What are its eigenvalues? Unitary Hermitian. So either plus or minus 1, right? Everybody sees that? It's plus or minus 1, right? So what that means is we can always choose US to be of this form. 1, 1, 1 of P entries and minus 1, minus 1, minus 1 of Q entries. Sorry? Any P and Q? Yeah, there's a constraint, right? P plus Q is equal to L. So how many distinct choices are there? Sorry? You again walked into my trap. It will not be L distinct choices. For example, if I choose L minus one of them to be plus 1 and the other one to be minus 1, that is actually same as L minus one of them to be minus 1 and one of them be plus 1, because that's again just multiplied by minus 1. Right? So there is something like roughly something like L by 2 choices. Roughly, it depends on L is even now. Right? And this is absolutely fantastic now, right? Because under the action of this on any state, what will happen? If you give me a column vector, when I act this on the sublattice, acted by the sublattice operator, what will I get? I will get these P elements of that state to be same, and the Q elements will get a minus sign. So it's like I have divided my set of orbitals into two types. One of them which quote unquote doesn't see this, and the other one picks up precisely a minus sign. Okay? Alright? And you can go further with this. So now let us see what is the symmetry condition. Right? What is the symmetry condition? Symmetry condition is you have to just recall, it is minus US, no change here, it's just H, right? US dagger is equal to H. No star, no nothing. Right? And so what will be the matrix representation here? Matrix is simply US. There's no complex conjugation. So look at this. This is again working out very nicely. This is as an operator, it is an anti-linear operator. But its matrix representation, because it's transposing, is linear. Everybody seen this? Okay. So that's NSI. Okay. So this is what we find. Okay. So let's just push this and find out what is the structure of the Hamiltonian. Right? Okay. Okay. So you see, I have some p orbitals and some other set of q orbitals, right? And what I'm going to do is I'm going to write my Hamiltonian in an appropriate basis. So I'm going to call this HQQ, HPQ, HPP, HPQ, and this has to be H dagger PQ. I will just write like this. H dagger PQ will be a Q by P matrix, right? And this will be HQQ. This is a general form of the matrix. I have not made any assumptions. I'm simply writing it out like this because I know that there are P's one kind of orbitals and Q other kind of orbitals, right? So let's just hit this with that. So this is 1P, 1Q, 0 with a minus sign, 0. And I need a minus sign here, which may get blocked for the folks on the other side, but there's a minus sign, right? And then again, 1P, 0, 0, minus 1P. And this must be equal to the same thing. That's a symmetry condition. I'm now trying to find the space of all Hamiltonians in class A3. What is the solution of this equation? I'm trying to solve for H. So the conditions that will be forced on you is that HPP is equal to 0 PP and HQQ is equal to 0 Q. What does that mean? The Hamiltonian looks like the following. You see that? So this is what Jay had used to say that there is sublattice symmetry. Right? So we can start from first principles and actually get to this. So what is the sublattice idea? The sublattice is there is a transposing anti-linear symmetry as an operator. What that does is, if you want to implement that symmetry, you immediately see that your one particle set of orbitals have to come in two different kinds. And what labels that kind? It's this P and Q. Right? So if I have L orbitals, the system can choose whatever size it has. So if I have an L orbital system, then there are some L by 2 distinct types. So a bunch of those will be called one sublattice. We don't have any lattice or anything, just some subset of orbitals. And the other set of orbitals, on one of them, you will see that the sublattice operation will give you a same sign. On the other one, you will get a minus. Okay? So actually it turns out that this operation is actually an extremely important thing in the whole Lie algebra game and so on. So if you are familiar with this, it's okay. Or if you have heard this before, such things are called as involutive isomorphisms. So square is identity, it comes back to itself, right? So These are isomorphisms of these vector spaces, and they're involutive. They square to identity. So it's very crude. These things are very, very important in identifying coset space and all this. So this is actually very, very nice connection. Okay. Any questions? So what is the dimension of this space now? What is the set of all? So I found out that the Hamiltonians in this class, this A3 class, have to look like this. What is the dimension of the space of all Hamiltonians? Sorry? Right, but is it PQ? 2 PQ. Why 2? Yeah, they're complex numbers. Okay, excellent. So it's 2 PQ, as is labeled there. And if you see what is that space in terms of the basic Lie algebras, you will see that you're taking the full Lie algebra of this, which is, so I'm writing here, this is IHA3, the space of all of these guys. What is this? You take the full Lie algebra of these guys, right? What is that? That is UP plus Q. And what am I removing from it? I'm removing this Lie algebra out. I'm removing the Q by Q Lie algebra out. Right? So take a direct sum of these guys. UP, direct sum, UQ, and complement. Right? Everybody has understood what is the origin of chiral symmetry? So this is the chiral symmetry. Right? This is how it all comes about. It comes out because there is a possible symmetry in these fermionic systems, which is this antilinear transposing symmetry. Right? And that's what we'll get out of this. Okay? I was hoping for a little bit more excitement. Happens. Yeah. Because I think in the high energy literature, this is exactly the chiral symmetry. The right movers, left movers being flipped. Okay, any questions, anything that you need clarifications on? Okay, yeah, is that a question? All right, okay. So now let me show you what is going to happen. Okay, 47 minutes, okay. Let me show you what's going to happen in the rest of the classes. I will be very brief. I will not get into the details of this. So in the rest of the classes, somebody had asked me that, can you find simultaneously what happens to UT, US, and all that stuff, right? In the rest of the classes, you will see that all three are there, right? And that actually forces some extremely interesting constraints, which because of lack of time, I will not be able to go into this. So in the rest of the classes, what happens is the following. I have these three symmetries, T, C, and S. Right? In the remainder of the classes, in the type 3 classes. And now I also know that there is this solitary business, right? That in each of these types, there is only one kind of symmetry. So whenever you have all three of them, you can always state the following correctly. This will always be correct. Right? Because the product has to be the third symmetry, and there's only one of them, and it has to be equal. Okay? And what this will do for you, with a little bit of algebra, you will see that US is equal to UT UC star. Okay, this is all algebra. You can show that with all those definitions that we have given, you will find that this US, the matrix corresponding to the sublattice, is actually a product of UT and UT star. And you can see that the antilinear nature of one of these guys have showed up. Right? Okay, you can do this. Okay, then what is the game? So, what we will do is in all of these classes, in all of the so-called chiral classes, the ones that start from A3 downwards, we will use US to be this very natural, this guy, 1 PQ. Right? We will use it. We'll use it for given. And then what we will do is we will be able to solve for UC from here. Right? You can just do an algebra and you can find UC. I don't recall at the top of my head, but it will be something like UT star US or something. Or maybe just check this. Right? Something like this you will get. Okay? So if you know US already, because we are in the chiral classes, then the goal is now reduced to finding UT. And once you find UT, once you find UT, US is already, UC is already given to you because you just find the product. Okay? And to do this, you have to play some little games here. And let me not get into the details of that. And instead show you, if I'm able to, okay. Yeah, and show you what is the result. Okay? So some very nice things come out of this. So in this class, which is called as BD1, you will find that, again, this L will be equal to P plus Q, right? And this UT will be, you can choose UT to be identity. US is always, all these are just forced to be identity, are forced to be 1P comma Q, right? And what you will find is that this UC is also 1PQ because you can see that that equation is automatically settled, right? Okay. When I go to this class C2, where both of these guys are -1, right? Something fantastic happens. You will find that this guy is like one of these guys, right? On the P, on one set of orbitals, you will find that the time reversal acts as if it is J. What that means is that P itself must be an even number, right? So P must be 2R, right? And Q must be an even number. And time reversal will not mix these orbitals. So that's how somebody had asked me, like, can we get it all nicely done when all three are there? And the way it's getting done nicely is that they don't mix these orbitals. They leave. So if I have this particular case where both are the same sign, that is both P and C are +1 or -1, under the action of this time reversal or charge conjugation, the orbital will go back to themselves, the same sublattice class. Okay? That's what happens. Okay? And you'll see the charge conjugation is this, and the other is that. Now, when I go to the case where they are opposites in sign, so here, for example, T is +1 and T is -1, something magical again happens, right? What you will find is that you can realize these kind of symmetries only in those classes where P is equal to Q. And in those classes, this time reversal operator, what it does is, it takes everything from one sublattice, and when time reversal acts on it, it will go to the other sublattice. You see? It goes what is called as F. F is the generalization of sigma x. So I'll tell you what is F. F looks like this. So F is this, 0, 1, 1, 0. Right? It flips. That's why we use the word F. Right? And the other guy will be J. J again will take everything from the A type to the B type, if you like, and so on. And when you go to the -1, 1, you see they kind of flip roles. They kind of change roles. This, and so on. Okay? So now you can use this entire machinery that is there here, and you can again work out what is the structure of the Hamiltonians in each one of them. And what you will find is that in these classes, you will find that the Hamiltonian looks like this. You will see that there are various kinds of things. So you can see that starting from here, something will get removed. Right? So this is the tenfold classification of non-interacting Hamiltonians. Right? Okay. So I will pause here and take any questions. So now you know the structure of what is the structure of the Hamiltonian in any class. Right? So if you want to construct a model with a particular symmetry, you know what to do. Okay? So this picture, this is an important picture. This is also an important table because it tells you what are the symmetries and how they are naturally represented in each class. Okay? Any questions at this point? Yeah. Okay. All right. So you're asking why am I doing this to be CT and TC and not equal to CT, right? Okay. Can you please hold on? Okay. That's a great question. In fact, CT will not be equal to TC. Apart from a phase, right? Exactly. So what is going on there? So you're now starting to think like, what is going on, right? So first of all, is everyone comfortable with the fact that t square is -1? In fact, the AC shut itself off when I asked this question. Is everyone just very comfortable with the fact that t square is -1? Okay. I used to feel extremely uncomfortable, and in fact, whatever I'm going to tell you now is a result of trying to get over that discomfort, right? Okay. So this actually goes to the very ideas of quantum states and all that stuff. So let me just go through this. I'm going to show you that this entire table can be obtained from very simple but somewhat sophisticated considerations. Okay, that's a little oxymoronic, right? Yeah. Simple meaning technically not difficult, but conceptually, technically not difficult, but conceptually a little bit, involved. Okay. Sorry about that. Yeah. Yeah, okay. All right. Okay. All right. So this idea is the idea of this cohomology. And to motivate what is the idea of cohomology and all, I have to first tell you something that you are very familiar with in quantum mechanics, right? So quantum mechanics right? So suppose I give you a state psi. Right? You can calculate any observable on that state by taking, the usual matrix elements and whatever you want, you how to do this. But suppose I give you another state, e to the I phi, where phi is any phase. Right? You will still get the same answers. Okay? So just remember this. This is something that we have seen many times before. Never bothered to take it in, take it in some deeper way, but it's there. It's an extremely important thing. Right? Okay. So this is a fact which we have used to. Okay, just keep in mind. Okay. So this is the fact that I will use. Okay. Control-Alt-Del, we are going to start afresh on some new topic. Okay. So I have to discuss what I'm going to do for the next 30 minutes or so. I need some background, for sure. Right? And the idea is the following. The idea is, I have a group. Right? Let me call that group as G. Right? So this has some elements G1, some set of elements, some Gn, something. Okay? For our purposes, we'll be happy with a finite group. Okay? So the question is, how do I represent this group? Right? And that's an important question in many contexts. I need a good piece of chalk. Okay. So how do I represent this group? What do I mean by that question? So typically, suppose I tell you that I have, suppose I take a triangle, right? An equilateral triangle, a nice triangle, right? What is the set of symmetries of that triangle? So you could rotate it by 120 degrees. Right? There are 3 of them, 0, 120, and 240. And then you could take the triangle and take that diagonal, right? And then flip it around. You'll get back the triangle, and there are 3 of them. So this is a group of 6 elements. Right? So I just told you that this is the symmetry of the triangle. Right? But this group of 6 elements can also be viewed in a different way. It is the group of permutations of 3 things. Right? So what did we learn by this short discussion? So there is some abstract group called S3. That group is called S3. The symmetry of the triangle is a realization of that group. That it is acting as a permutation on something is another realization. You can find bazillion other realizations of this. Right? This is like saying, what is number 2? Right? You see, the 2 is the abstraction of everything that is 2. Okay. So now suppose I want to use this idea that it is so I could, for example, to study this group S3, the abstract group S3, so I'll just call it the permutation group 3. This is the permutation 3. suppose I want to study this group. I could just use the triangle and see how the group acts on the triangle. So for example, I could take some set of vectors, like two-dimensional vectors in a two-dimensional space, and I could write matrices associated with each group element, which will act on vectors and transform them in certain ways. Okay? So what I'm going to do is I'm going to take this group and associate it, starting from this group, I'm going to write for every group element a matrix. That matrix will act on some vector space. Right? In what way? So there's a representation space. Let's just call it V. Okay, V we have already used, so let's call it W. Right? So what happens? So this has some vectors, let's call them W, some set of vectors, if you like. Right? So this is, we are going to use, right? And associated with each of these group elements, there is some kind of linear operator that it will act on this vector space. Right? So what I'm going to do is I'm going to make a map from G. G goes to some matrix. So this acts on this. Right? So it will transform vectors. Every group element will transform vector. For example, this 120-degree rotation I told you. If you act 120, just take all vectors in the two-dimensional plane, just rotate them by 120. That will be the matrix representation of that. If I want to flip about some axis, suppose I want to flip about the x-axis. Suppose my triangle were placed like this. I want to flip about the x-axis. It's the transformation like 1 minus 1. Right? All the y's will go to minus y's, and the x's will remain the same. So you can see that every one of these group elements can be represented by a matrix. And there is a space on which you can act. Okay? All right. So everybody has understood what is a group representation? So if I just do this, it's not enough. I have to enforce some conditions. I have to enforce that the group multiplication table is respected. Right? So I have to enforce some group multiplication table is respected. So for example, D of G1, G2 must be equal to D of G1, D of G2. Right? This looks like a very simple result, but it's very important to understand what's going on here. This G1, G2 is the abstract group multiplication. So it's a new group element. G1, G2 is a new group element. There is a matrix associated with that group element. That's what this D of G1, G2 is. That matrix is equal to the matrix associated with G1 multiplied by matrix associated with G. Right? So what that means is, if this group had a multiplication table, if you write the multiplication table in terms of the D's, they will be faithfully reproduced. That is not to say that all the D's will be distinct. Right? If all the D's are distinct, that for every G, there is exactly one D, there is a unique D for every G, that is called as a faithful representation. Okay? That means there is a, so D of Gi is unique to G. So can you tell me a representation which is not unique? Okay. All the matrices are identity. That will satisfy the multiplication table. It's a very nice multiplication table with 1 everywhere. Right? But that's not a faithful representation. Okay. Let's look at some examples, somewhat less trivial examples. Okay. Consider the group U1. Everybody knows what the U1 group is, right? It's the phase. Very important in quantum mechanics. What is the representation for this? Sorry? So what is the space? So you have to tell me what is the vector space and what is the matrix. Exactly. Thank you. So the vector space is W is C, right? And D of some element here. Let me just call that element abstract element theta. The abstract element theta. It's It's not the angle theta, some theta, right? And this is e to the I theta, where this theta is a number corresponding to that. Right? This is the representation. Okay? Is that the only representation? Sorry? No. Why did you say that this is the representation? No, but what is your, people are saying that I'm not, this is mathematical and all that. There must have been a physical motivation for you to give this e to the I theta, right? I erased what should be kept in mind. Right? This is that U1 phase symmetry, right, of that we had, of the wave functions. Right? So this U1 would be that group that represents that symmetry. Right? So if I have any state, that's a one-dimensional vector space, and whatever phase I'm multiplying with it, it will not change the physics. So that's this. Do you know any other context in which the U1 group shows up? Okay, I should keep track of time. Yeah. Do you know any other context where U1 group shows up? Okay, how about this? Take this. Rotation about some axis. Right? That is also a U1 group. Can you write a representation for that? Sorry? So again, everyone is thinking in terms of real spaces, which is fine. I mean, which is not fine. I'll show you another representation of U. This is actually a two-dimensional representation. And the representation is this. D of theta is equal to e to the I theta by 2, I think. And then e to the minus I theta by 2. It's also a representation, but you will see that I'm actually cheating here. Right? This is just the rotation of a spin half about some axis by some angle theta. This is exactly that. Right? It's also the U1 group. Okay, everybody has seen. Okay. Now, what is the difference between this representation and this representation? Of course, this dimension is different, right? But I am also introducing this representation for a very specific reason. You see that this representation has a very funny structure. For all elements, these guys are actually 0. So these are actually two copies of a two one-dimensional representation just glued together artificially. Right? So such a representation is called as a reducible representation. So if you give me a representation, and if it can be broken down into representation of smaller dimensional vector spaces, that would be called as a reducible representation. Okay? All right. Now what you have to do is you have to open some pages of some famous books and read the first few chapters, and then you will get inspired. Right? So for example, if you read Wigner's book on quantum field theory, right, he will show you that all particles that we talk about, they are actually irreducible representations of some symmetry. Right? So for example, you should read about this. We are going to use exactly that same idea to find, I start with these intrinsic symmetries. What are the irreducible representations of those symmetries? Right? That's the question we are going to ask. And that will give us the answer as to what matter is allowed. Right? And we are going to demand them to be fermions. So we'll sew that in. Right? And that's what we're going to do. And we're going to find these tenfold classes coming out of irreducible. Okay? I made a major step forward, which is that I'm saying that there are symmetries, and whatever objects that we are going to be working with, the stuff, our microscopic degrees of freedom, they are of course described by some vector spaces, like the state kets and all that stuff. They are actually representations of the symmetry. Right? So I don't know, somewhere I've read that God made man in his or her form or something. So actually it's groups made. Everything that we are made, we are just representations of some groups. It's true. Right? It's absolutely true. Right. That's a that's a semantic point. And the tenfold way comes out, and oh, beautiful, Krish. Thank you. What beautiful, the high point of the school. Oh, we have actually explained what is the origin of the 10 avatars. I didn't realize this. Krish, I should talk to you more. Okay, great. All right. There is a fly in the ointment. Did you see the fly? Okay, there is some subtlety here. So this would all work fine for, see, so if you take any book on group theory, they'll give you some ball spring model connected, and they'll ask you, find all the eigenstates, eigenvectors, degeneracies of energy levels, all that stuff will be done. That's all fine, I mean, that's all good. But if you want to do quantum mechanics, you have to generalize this idea of representation. Okay? So if you want to do quantum mechanics, again, it's all Weinberg's book, Quantum Field Theory, first chapter. You need a concept called projective representations. Right? So what is this idea of projective representation? Right? So the first thing is, again, you have this group. Okay, the group has been erased, sorry. There is this group G. So it has elements G1, Gn, if you like, right? Okay, we can write like G1 mod G. This is the number of elements G, right? And associated with each of these guys, of course, there's a vector space, and associated with each of these guys, there are these matrices Pg, which act on this vector space. Okay, what is a projective representation? The projective representation is this. dg1, dg2, what would you want this to be? In the usual way of doing things, you want this to be dg1, dg2. Okay, just let me hold on to my notes so that I will not deviate from the notation, so that I will not get confused myself and confuse you guys. I hope I've used the same notation. Yeah, it's good. Okay, all right. So let's understand what we are doing here. So this is some symmetry operation. I can act it on a state and see to what new state it goes to, right? So let me just start with some state. I'll come back to this. I start with some state. So first I'll go to some state, which let me call it psi tilde, right? Then I act on this. Then I'll go to some other state, psi double tilde, right? Now let me take this object and let me say that this goes to yet another state. So let me just call it psi triple tilde. What is the relationship you want between these two guys? It is equal is what you would have wanted to be. But you don't need it to be equal in quantum mechanics. You can always multiply it by a phase. Okay? Such representations are called as projective representations. Why is the word projective used? Because what you're doing is, you're saying that there are vectors in the Hilbert space. Take this, my hand should be viewed as a unit vector. This thing, you're not worried about. This is that U1 phase. The physics is only in the direction. It's not in this. Everybody understand? Yeah, you're looking very unhappy. Yeah. No. Don't get into the math. We'll do the math. I've left gap here to fix the math. Right? No. Just demand let's look at it from the physics point of view. So I do these things, I go to a new state. I have this one matrix, I apply on it, I may get another state. Right? But how different can they be? They can only be different by a phase. In the previous case, we said that phase difference has also to be 0 or modulo 2 pi. Here we are relaxing that. We are saying no. So now you see t square equal to -1 makes sense. You see, because t square is dt, And you would have wanted it to go back to identity because I'm doing time reversal. So we were taught that time reversal means change t to minus t, time to minus t. If I do it twice, I should come back to whatever I have, right? But I don't, I go to t minus 1. But that's absolutely fine because it's projected. And what we showed is that if it is t, projectively also you can have only 2 of them. It can be at the plus 1 or minus 1. We want to understand where that comes from. Why couldn't you have e to the pi by 4 times? That's what we are trying to understand. That's the whole game. All right? Okay, good. So what needs to happen for fixing the math is that there should be a complex number, unimodular complex number, right? Omega G1, G2. Right? So omega is in what? Unimodular complex number. Right? Everybody's good, it has to become a phase. Such a representation, that is, you start from the group and write out matrices. When you multiply matrices corresponding to the product of groups, they will not come out to be exactly equal. They will get multiplied by a phase. How many such phases are there if the number of elements in my group G is mod G? I mean, this is a very standard notation. Number of elements. How many such complex numbers are there? Sorry? Why did you choose 2? Omega depends on D1 and D2. How many G1s and G2s are there? How many G1s are there? There are mod G1s. How many G2s are there? Mod G. We are not making any assumption about the group being abelian, nothing. Right? So these omegas, G1, G2, there are mod G square of them. So projective representation not only gives you the matrices, you have to also get these complex numbers. Actually, the precise way to state is you have to first specify these complex numbers. Then I have to ask which are the matrices that will satisfy this. Absolutely. Right. Yeah. We will look for faithful representations. Right? Okay, generically no. But from physics perspective, certainly we want faithful representation. No, you can have unfaithful projective representation. That's okay. You can, but we will not worry about that. We will look for faithful representation. Yeah, question? Yeah, okay. So, okay, just as Krish anticipated, if I simply state this, it's not enough. Right? I have to give some additional conditions on what these omega should be. Right? Can you guess what are the additional conditions? If you have seen this, just relax for a few minutes. If you haven't, it's a very good exercise to figure out what are the additional conditions. What are the additional conditions? Okay, we need to take a good guess. So group multiplication has a very important property, which is it is associative. So you want that associative property also to go into this. Everything is okay, Shubha? Okay, so you want that associative property to also go with this. Okay? So how will I include the associative property of this? So what does that mean? What do you mean by associative property? Associative property means, everybody just recall what is associative means. G1, G2, G3 is equal to G1, G2, G3. This is absolutely necessary for you to form a group. It's set in stone. You cannot change this rule. Right? Okay? So if I write out these matrices in this way, we want to demand that it's also associative. Okay? That will force on you a following condition. Right? What is that condition? Wow, bad news. The condition is the following. boy. The fact that I'm not a young scientist in this country is hitting me now. Good. I got it all right. G1, G. Okay? All right? So there is, just take a look at it. Just make sure that you understand what I have written there. Not the content of it, but just the sequence of things. Okay. So you see there are G square of these guys. Right? So how I arrived at this result is by starting from this, writing the representations, and taking this and writing D of these guys, and doing it in two ways. The first way is this, and the second way is that. Right? Okay? Come. Right, exactly. So I have to explain what that means. So what I am allowing for in this entire game is that these matrices, because I'm doing quantum mechanics and I have all this Wigner idea here, I'm also allowing these matrices to have anti-linearity. Okay? So if these group elements have anti-linear character, if we believe that physically they should correspond to anti-linear symmetries, then they have an action. The group elements themselves have an action on an element in U1. The group element itself can talk directly to U1, right? And what that means is the following. So for example, if G1 has an anti-linear character, right? So imagine that were the abstract, really abstract time reversal operator of the theta of the Klein group. Then associated with this will be, so when you do this sequence, this will be replaced by complex conjugate. Okay? So I can, if people have understood it, it's okay, I can proceed, right? So what that means is, I can say it a little bit more technically, if you like. See, omega G1, omega G generically, is a short form for the following thing. Associated with every group element, there is a function, phi g, which takes you from U1 to U1. Right? There is a function, for every group element there is a function. Right? In our case, that function is complex conjugation. And that function should be bijective on U1. It should give inverses. And it should also satisfy the following very nice condition, which is that phi G1, G2 must be equal to phi G1, phi G2 of whatever, if it's acting, if I take omega to be, or x to be an element of U1, phi G1 of x should be equal. So can you state technically what this means? Okay, technically it will be said that this phi is a homomorphism from the group to the group of automorphisms of U1. Who wants to pick an auto right now back to? It's a homomorphism because group multiplication table is respected. Huh? But so which group are you starting from? You're starting from G. For every G, you're giving me a function. The function is on what space? It's on U1. Space U1. And it's an invertible function. So it is a homomorphism from the group G to the group of automorphisms of U1. Because a set of all invertible functions of U1 form a group by themselves. Right? I think it's reasonably clear, right? Okay. Exactly, for our case. Yeah, for our case. So omega G will be, in our case, precisely. Thank you. So in our case, omega G will be either omega or omega star, depending on what is the G. Right? But I'm sort of introducing the very general framework because you see, if some of you are interested in following the theoretical developments in the field of what happens in interacting topological stuff, you need this because everything there is projective representation. If you want to work in conformal field theory, whatever that game is, you need all this. Right? This will not be useless. Right? Okay. All right. Okay. Yeah, I have only 10 minutes. Yeah. Okay, this is what you get. Okay, so what have I specified? I have specified this multiplier system and these two things, right? These two conditions. I have specified this multiplier system. It has to satisfy this, and I have defined what is that condition, what is that function. Okay? Now I ask you the following question. I give you a group. How many distinct multiplier systems are there? Why is this question important? Because that will tell you all the projective representations of that group. Right? And if we choose faithful representations, we could actually discover, starting from the group, what all can exist. Right? So the group of symmetries, what all can exist, we can just discover that. Okay? So the question is posed, I hope clearly. I give you this group, and I ask you, and I give you this function, this phi of g. What are all possible multiplier systems that can have? By the way, this is called as a multiplier system. It's called as Schur multipliers. You'll be very interested to know that all of this was done before discovery of quantum mechanics. Right? It has got to do with conformal transformations and all. It has got to do with geometry at the end of the day. Right? Yeah, Schur actually asked these questions in that context. Okay, so these are called Schur multipliers. So the question I want to ask you is, how many distinct Schur multiplier tables are there? Okay, that sounds like a little bit of a difficult question. All right, now I want to show you something very, very interesting. Yeah. Abstract group G. Yeah. Yeah. What's the multiplication table? Yeah. Phi G is given. Because you have to know what is the nature of that group element, each group element. Or not, exactly. I'm asking, suppose I give you the group G and this phi's, how many distinct omegas are there? How many distinct set of these kind of multiplier systems that satisfy this condition, this condition? How many distinct things are there? But they will not all satisfy. So if you take arbitrary, this is exactly what Krish was asking. If I take arbitrary number of G square number of elements of U1, they will not satisfy this condition. How many conditions are there? Tell me, how many conditions are there? I want to determine G square objects with G cubed conditions. Okay, it looks a little strange. Yeah? Okay, let's see what we can do. Okay? Actually, we have the help of really, really stellar people in the field like Schur and all. They did all this stuff before 1920s. So this is all very old stuff actually from mathematics. Okay. So here's my first statement. To try and answer this question, statement 1. If omega 1 is a multiplier system, Schur multiplier, say Schur 1, and omega 2 is another, is the Schur 2. Right? I have one multiplier system, another multiplier system. Omega 1, omega 2 is a multiplier system. Can you see that? It's very easy to see that. Right? So omega 1, then omega 1, omega 2, which is equal to, let's say, omega tilde, is a multiplier system. It will satisfy all those conditions. Right? Right? You can show that it will satisfy that condition. Huh? By the way, this condition is called as the co-cycle condition. It's called the 2 co-cycle condition. Right? And there is a connection to geometry and things like that. Okay. All right. So this is the product will be this. Okay. Now you'll see, if you give me omega, a Schur multiplier system, just take omega 2 is equal to omega inverse. Omega 1 inverse. That is also a sure multiplier system. So if you give me omega 1 inverse is also a sure multiplier system. Yes? Good? Everybody follows that? Just close your eyes and just see. Right? Yeah. I mean, see see there. See inside your head. Right. Okay. Yeah, this is a recurring problem, right? Oxymorons and mistakes and all that. Okay. All right. Okay. So this is what happens. So what have I showed you? I've showed you that the product of two of these multipliers is a multiplier. I've showed you that a multiplier has an inverse. Now I will show you that there is a multiplier called E. What is E? All the omegas are 1. There is an identity multiplier. Everybody sees that? So there is a multiplier, all the omegas are 1. E, all the omega equal to 1. N square ones. So what have you learned by doing this? The multipliers themselves form an abelian group. Right? The multipliers form a group. Okay. So then it's very clear what I should do. I should find the distinct group elements of that group. If I find distinct group elements of that group, that will give me the answer as to how many multipliers are there. Everybody sees this? Right? And that group is called as the second cohomology group of our group G. So the group of multipliers, I will refine this definition in a minute, right? The group of multipliers right? It's not precisely true. I will make a correction to this in a minute, right? It's called as the second cohomology group. Right? And I will write it in gory detail. So this is usually called as H2. This is the group G. And I'm extending it by U1 because my action of these group elements was on U1. That function phi was defined on, for every group element I had an action on U1, right? And I have to also specify with that function, right? So there is a group here. Okay. Now you will find something very interesting. You will find that if you have any two group elements, they may not be distinct. Right? They may look numbers wise, they may be different, but they actually correspond to the same thing. Just like if I have a representation of a standard group in terms of some matrices, I could actually just do some rotation of that vector space and get new matrices. But that's not a new representation. It's just related to the old representation in some way. Right? In the very same way, there can be some relationship between these group elements, which I will presently write down. Right? So if I have multiplier system 1, if I have sure 1 and sure 2, right? If it turns out that this looks like this, okay? So if it turns out that if I take omega 1 and omega 2, right? Remember, these are n square relationships. That there is another function on the group G, which is called as A, and this ratio is always this. Suppose there is such a function for given omega 1 and omega 2, then they are actually the same. Right? This is the equivalent of very crudely, some unitary transformation of this. Right? So two such things for which there is a function from A to G. So A is again a function from G to U1. Right? If there exists such a function, for every group element there is another complex number, and the ratio of these two Schur multipliers is this, then it is these two are equivalent. Right? So I will say here, if this is true, then omega 1 is equivalent to omega 2. Right? So now I'm going to, yeah. Same, of course, same. That 5. Yeah, absolutely. Right. So now what I'm going to do is, the group of equivalence class. So all of these guys which behave this way, they are all grouped into one object. The equivalence class of these multiplier systems. That is truly the second cohomology group of the. Okay? So what is the game now? The game is, I start with a group, and I by begging, borrowing, or stealing, I find what is the cohomology group of that. Right? And that cohomology group, its elements will index the multiplication, the Schur multipliers. Okay? Everybody's good with that? Okay, that's the statement. All right? Okay, with that background, and with the red light flashing, and the organizers are not here, and none of you are, but Krish, you're interested in this stuff. Okay, all right. So with a little bit of stretch of the space-time, time especially, right? We will just proceed, and I'll try to conclude quickly. Maybe about 6, 7. Maybe I'll tell you the I'll give you the statement, at least. Okay, all right. I'll give you the statement. So what do we have? We have the Klein group. That was the set of all the abstract group of symmetries, right? So I removed all the usual. No, I didn't want that to go. This is a great message, no? I would have expected something subtle. Okay. Oh, then when they said stretch space, okay, all right, okay, sorry. All right, so let me just write this K4. I really needed that because I have to, yeah. Okay, if I write K4 has these following entries, right? I, sigma, I, theta, okay, I never remember notation, actually, unfortunately. I have to look at this, yeah. I, theta, chi, and sigma, and this is I, theta, chi, and sigma, right? And you have the multiplication table which I showed. Maybe I can just use this, no? I'm just fumbling around, sorry. Does anyone see where I kept that? Huh? Brilliant. Huh? Enter there, huh? Maybe we can just undo. No, it's not. I press return. Okay. Okay, good. All right. So this is the group. Okay. Our physical system. What are the allowed symmetries that it can have? This is the set of all possible symmetry, the abstract group of symmetry operations. That's what this is. So our system can choose to have the following cases. So since I've written this down, the symmetry group of system is either the identity, this is type 0, it has no symmetries other than just the identity. It can have what is called as Z2T, which is the subgroup of time reversal. You see, time reversal, the 1 and theta form a subgroup. Right? It can have this. It can have Z2C. That is another subgroup. It can have Z2S. Right? And the whole thing. Right? Okay, here's the statement that I wanted to prove, which I will not have time to prove. If I take the set of all multiplier systems of all these 5 groups I have written down, I get 10 classes. So the 10 classes that we have are simply the multiplier systems of these groups. They are the projective representations of these abstract groups. So fermions are simply the projective representations of these. I think it's a very nice message. That's the message. Right? Okay? So what we have done, if you can read our paper, you will see that we have actually calculated, so these groups are well known. Oh, I must also tell you the phi, right? So phi associated with identity, phi of x is phi of z is equal to z, and phi of sigma, phi of theta is equal to z star, because that's the time reversal, so it's antilinear. And in our representation language, since we learned that the charge conjugation chi, right, of z, that also is z star. And this guy in the representation is a linear operator, so that will go as a phi of sigma of z will be just z. Right? So then what we did, we used this thing and found these group multiplication tables. And look at the extreme nice thing. If I go to the Klein group, this guy, the K4, this is the last 4 of the rows that I had. Right? In the previous table, okay. Yeah, this is not working. All right. In the last 4 that I had, these guys, 1, 2, 3, 4. They had all 4 of them. Right? I'm going to show you the multiplier system for that. And Abbas, your question will get answered magically. Right? Okay. So this is the multiplier system that we calculated. All right. Okay. So this is when this Klein group is there. So what I've done is I've calculated this cohomology group for the Klein group here. And you see, the cohomology group is indexed, the elements of that are actually n square numbers, 16 numbers. And they're indexed by 2 integers, which are t and c. And they can take plus or minus 1. Right? So for example, if you take chi and theta and multiply, so this will answer your question whether tc is and ct will be same or not. Right? So this multiplication table. So if you choose, for example, t equal to 1 and c equal to 1, right? S is always 1 here, right? You will get a multiplier system for this. Based on that multiplier system, I find the smallest dimensional matrices, T, which will satisfy the group multiplication. And that will tell me all of these things can be re-derived, all of this whole table can be re-derived in the following way. You will find that class A has no multiplier system, it's just identity. So these are just n copies of a one-dimensional representation. This fellow is n copies, L copies again of a one-dimensional representation. Right? This guy is actually m copies of a two-dimensional representation. Right? And you can see this is very beautiful, right? So when you go to this particular one, C2, you will find that there is some irreducible representation for a certain multiplier system corresponding to what I showed you in the previous thing, this guy. This guy, just put -1 here. You will see that you can get a multiplier system. Find what are the matrices that will satisfy the correct group multiplication table, and you will find that they are these guys. So what do you see here? There are p copies of one particular representation and q copies of the other representation. They are all reducible representations. So what I have showed you here is that an arbitrary L orbital fermionic system, right, is a reducible representation constructed out of multiplier systems of the Klein group or its subgroups. So now we understand where fermions emerge and why tenfold comes from, where it comes from. It comes from the fact that this is what is allowed by the laws of whatever. Bosons, okay, thank you for that question. So how do I bring fermions here, right? So you see, when I brought okay, let me give you the answer to your question. I don't know. Okay, I don't know what happens for bosons. I'm a little bit confused about that. I know how to do it for hardcore bosons, but not arbitrary bosons because they can take any number of particles per state. Okay. But where I use the fact that these are fermions in this representation is the fact that I have this Hilbert space which has this structure of particle and hole. I've used that explicitly in the representation. That goes into the representation. So I have to find out what to do for bosons more carefully. Okay, but hardcore bosons, I think the same story will go with some modification. Because they have this constraint that they have also some particle hole sense. But canonical bosons, I don't know. Because every state can take any number of particles. So I don't exactly know how to bring this idea of particle hole transformation. Okay, so that's the message, and so let me stop here. Very quickly, in the afternoon, I hope I have uncovered some symmetry, not covered, right? And we will go from symmetry to topology. Right? And the afternoon's discussion will not be as, or what many people will say, boring as this, right? I say, for example, just to show you, I have things like this, right? And I have some rubber bands, and yeah, and I know that you will bring your own objects of favorite topology, like tomatoes and things like that. So we can actually create new kinds of excitations, right, with new statistics.